following. How is the relaxed micromorphic model doing in regard to chirality in metamaterials?
Yeah, this is a very good question, because for now, as you saw here, I will take, if I can, back the constitutive equation for micromorphic. You see here we all have fourth order tensors which appear. So it's a classical type elasticity tensor of the sixth order, sorry, of the fourth order. We don't have sixth order tensors intervening. So chirality was not treated for the moment, but we can think to kind of generalize the framework and try with symmetries of these elasticity tensors if we can catch such underlying symmetries at the micro level. So for now I would not have an answer on whether this can be immediately done, but including the opportune symmetries in the elastic tensors, then can be we can think to generalize.
Thank you.
Thanks. Do we have other questions? I do not see anyone raising the hand. I have a question regarding your way of recovering the band structure. If you can just, maybe just to start, the first question is regarding the mass density. You consider the mass density as being constant for all frequencies,
yeah,
right?
Yeah. Everything is constant, and it's the apparent mass density which enters our continuum model. So you make your average on the unit cell, and you fix it once for all once you have fixed the metamaterial. And this, thank you for the question, because I didn't point out explicitly. Everything in our model is constant, so it's not frequency dependent. And that was the interest, because for us, a material, even if it's a metamaterial, should to be characterized, that should be done with constant parameters, has Poisson model, Poisson ratio, and the Young modulus. They are constant, so we don't want them to vary.
Function of frequency, okay. But do you mind just to show one of these dispersion relations, such that I can ask directly?
Okay. You mean here?
Yes, for example. Okay, then you said basically the way you recover this, the different bands, that you are also using the cutoff frequency, like here, omega R, omega S, omega P.
Yeah.
And how are you sure that this, I mean, imagine I would have some more local resonance inside of my material along more or less the same values of omega of the frequency. How would you discriminate these frequencies, and how would you remove them, or will you take them into account?
No, we take them into account, because here local resonances, you can see here you have a quite almost flat curve also in the Bloch-Floquet curves. So it's just a question. I don't look what's happening for k greater than 0. I reduce myself to k equals 0. I have some values which are given by the Bloch-Floquet simulation. I need a numerical value. And on our hand, on the relaxed micromorphic hand, we have formulas. We have omega as functions of k. We restrict to k equals 0. We have some expressions in terms of our elasticity parameters. We impose algebraic equations and with the numerical values on the right-hand side, and we reduce our number of free parameters. So, of course, at a given point, you will have more curves. If you go ahead in frequency with Bloch-Floquet, we don't have enough degrees of freedom. In that respect, we should make something which is even kinematically more complex. So you introduce your P and another tensor Q, so you can get higher in frequencies. But for now, we would like to understand a little bit better what's happening for this range of frequencies.
Okay, thank you. We have more questions. Just don't forget that your microphone is off and you have to switch it on if you ask.
I've got one question actually. So you say that your parameters are not frequency dependent, and essentially if you have higher order gradients in your theory, you can go up in frequency. This is what you say?
Yeah, we can, with higher gradients only, we can get higher in frequency, but not very much. If you just have second gradient,
yes.
If I find, yeah, here. If you have second gradient, you are restricted here to the green region. So you get higher in frequency. You start catching some dispersion, but that's it, because the kinematics of a second gradient continuum is the same as Cauchy. So you only have the displacement. You can only have two branches here. You cannot get the optical branches. So for more branches, you need to extend your kinematics. So introduce this micro distortion, and etc.
And your micro distortion, my understanding is that it is not classical homogenization.
No. This is our point of view is to get directly at the homogenized scale. So what I presented here is already homogenized. Actually, that can be done with not respect to any specific microstructure. Okay, the identification comes later. Once we have our homogenized model, we want to know, does it work for some phenomenon? So we take one microstructure or the other, and we make an inverse fitting approach on that specific microstructure.
Yes, this is my point. Is it, can you deduce this equation in some kind of logico-deductive way, you know? Because, okay, you assume some kind of set of equations and you force your set of equation.
Yeah, we start saying, yeah, we make some considerations of the type, okay, now I have a general anisotropic micromorphic model. I want to fit it on a tetragonal metamaterial, as it was the example. So we are going to take our elasticity tensors and restrict them with symmetries to the tetragonal case. We make these ansatz that the symmetry class at the microscale is kept at the macroscale. So our tensors have a tetragonal symmetry, and with this, then we fit back to our material. So this is the way of making a connection to the microstructure.
And can you go back to the microstructure? Because I did not really understand what you meant by, you know, choosing your unit cell in an arbitrary fashion. It's one. You know, you have a periodic cell and you choose. Yeah, I would like to hear that.
Yeah,
again.
yeah.
So.
Okay, this was part of the procedure. I mean, here you see you have the cross-like, which is the natural one that comes to you. But then also if you take the other yellow one here and you reproduce it, you have the same metamaterial. And then here also, if you take this cell here and you reproduce it, of course, if it's infinite, because if it's finite, you have different boundary conditions, of course. But we are talking about an infinite block. You can have infinite ways of recovering the same metamaterial with different cells. And the point is, okay, we just restrict to these four, which keep the tetragonal symmetry. If you take, for example, this one, it's not tetragonal, but if you reproduce it, you get the same metamaterial.
What I have some difficulty to figure out is how come you have some extra information by changing your unit cell, because this should be all equivalent I don't understand this.
The point is,
Yeah.
we want in some way a posteriori relate our C micro tensor. Maybe your microphone, I have, thank you. We want to relate in some way to the microstructure. We know that this tensor is related to P, which is related to the microstructure. So we want to go to the unit cell, but there is no unique way to go to the unit cell. For example, if I take this 4 and I take simulation, numerical homogenization, and I put displacements. If I put displacements on the boundary, I will get to the stiffness of the unit cell. So I'm not making it periodic. It's just on the unit cell. It's micro. I put displacements and I assign them, and I get the stiffness as a result. And this cell will be stiffer than that. in that
okay. This is what I did not understand. So you don't have periodic conditions. Okay, that's the point. Okay.
So we test 4 cells and we take the stiffest in some sense, and we say our C micro is equivalent to the C that comes stiffer from this experiment. Of course, that could be not the exact value of C micro, but it's an estimation, which is a good first estimation. And it worked in the end for this metamaterial. If it shouldn't work, we should arrange the C micro a bit also on the dispersion curves. Yeah.
But wouldn't this be equivalent to just keeping one cell and just having some phase shift between the opposite edges? Is it?
Yeah, but this is the case. We apply the displacement field on the boundaries. So I don't know if it's...
What I'm thinking is maybe it's what you're doing is another way to reproduce what the Appliquées theory does.
That's possible. That's possible. Should be...
Because Craster in his high frequency homogenization essentially compared with classical homogenization is just that it takes into account the the change of phase of maybe this is related because essentially perhaps because and theory behind what is there a theory behind? There is a theory of this. There is some rigorous explanation. I mean, there is a...
No, this is a procedure we invented to relate our micromorphic parameters to the unit cells. We had to have some guess about this C micro, so we took this approach. Actually, of course, if you take one unit cell with kinematically uniform boundary conditions, this is well known. But this way of isolating cells, we also tried to impose forces on the unit cell. But eventually, if you take this cell and you put forces on the boundary instead of displacement, and you compute the stiffness, you get a lower stiffness than if imposing displacements. And here we wanted the stiffest possible C micro, because we know that in micromorphic, when we get smaller, we get stiffer. So we wanted a way to pick up the stiffest micro behavior.
If I can just make a remark regarding, I mean, I'm not sure to understand perfectly the way you impose the boundary conditions, but generally, if you just aim to compute some property like the Poisson's ratio of such structures that are on the two on the bottom of this right part.
Here?
We actually don't see what you are pointing.
No, I'm not sure I got the question, sorry.
So the point is you cannot just apply forces. You have to apply forces and displacement.
No, either force or displacement.
Yes, but then you are violating somehow the infinite conditions.
Yeah, exactly. We are not infinite. We are here just on the unit cell. We are not making periodic homogenization. Periodic homogenization was for the C macro. Here, for the C macro, we get periodic. We make what we are thinking about. We make a cell and we reproduce this periodically. And in this case, there is no problem if you take one cell or the other, because in the limit, you will have the same result. Here, the point is, we want to stay on the unit cell. We have one unit cell, we impose boundary condition, and we solve the elasticity problem for the unit cell, not getting periodic.
Okay.
And with this, we get the stiffness, and we want to pick up our departure point was this. We want to pick up the stiffest possible response at the cell scale. Maybe this is...
But question mark, maybe you could just also consider a larger cell. What happens if you, instead of having just element, you have 2 by 2, you have 4 elements, and you apply, and then, you know, 3 by 3, and then 4 by 4, what happens?
It happens that then you will have a less stiff response than you have on the unit cell. Here is the point that we have in the theory of micromorphic media. We know getting smaller, we get stiffer. And we have a finite limit for this stiffness. And the point is, which is the value of this limit? Somehow we want to figure it out on this metamaterial. We don't have a unique answer. Maybe this is still to be improved. We don't know. We just tried to pick up unit cells, because going smaller than a unit cell does not make much sense in a first instance to us. So let's stay on the unit cell. We see that we have different stiffnesses if we take this or that, and then try to pick up the stiffest possible. And let's try to say that our C micromorphic is this response which is coming from the stiffest unit cell. That was the guess. For this case, it worked. For other couple of cases we are analyzing now, it works pretty well. And then, is there a better way to do? Maybe that's, we still need to discover.
Thanks. Do we have more questions?
Hi, could I ask a question, please?
Sure.
Of course.
Hello.
Yeah, so hi, Angela. It's Marcus Wheel from Strathclyde University in Glasgow here.
Hello.
First, it's actually a comment and then a question. The comment is, I'm encouraged by seeing that somebody is trying to identify the constitutive parameters in the dynamic regime.
Mm-hmm.
In some respects, this strikes me as more beneficial than in the static regime, because you don't necessarily have to constrain your test piece in the same way when you're doing it practically.
Mm-hmm. Mm-hmm.
So you negate some of the difficulties that you actually encounter when doing it statically. But following on from that, you showed us an image of some samples in one of your slides.
Yeah, the experimental one, you mean?
Yeah, the experimental ones.
Yeah, but we didn't really test those one, you mean?
Right. The question I have comes about where you define the boundaries of your sample relative to the boundary or relative to the unit cell. So on the left there, you've got a sample in which the boundaries bisect the unit cells, don't they? And on the other one, they're on the edge of the unit cells.
Uh-huh.
Would you expect any difference in the behavior?
Yeah, for sure.
Yeah.
I mean, if we stay to this or that metamaterial, for sure we would have some different boundary behavior. But for now, what we did is this we didn't test because it's too small. You see, it's like very small, so to take the dynamics or plane wave inside this, it's not possible. But what we are doing with Emmanuel Collet at École Centrale in Lyon is to take a reasonably large specimen of this, in this case, this one, and see if we apply a pulse in the middle, what happens. And it looks that for now we have encouraging also matching with the experiment.
Right.
But for sure, close to the boundary, if you take this or that, that should change a little bit. Yeah.
Yes, perhaps I have a question, if we have time. Agnès Morel from Institut Langevin.
Oui, bonjour.
Bonjour. So a quick question. There is a transparency where you showed the feet of your parameter. And I think that you mentioned that there is two angles.
Yeah. Mm-hmm.
So what does it mean? It means that the fit is done with the data of two angles, or that the fit is different for each angle?
Okay, so we focused first of all on the normal direction of propagation, and we started fitting on that. But then we maybe had one left parameter. Now I don't remember exactly, but we have some one or two extra parameters that we fitted also on the second picture. But the point is, with this tetragonal symmetry assumption, then all the angles between the two are automatically fitted. The information about anisotropy is intrinsically contained in the model. So
which means that if you take, so you take the incident, the normal incidence, and then if you take any angle, you will have the same answer for the...
Yeah, we have the correct answer with the micromorphic, and maybe it was a little bit too quick, but I tried to show it in here, because here in this picture you have the y-axis is frequency, and then you have the angle of incidence on the x-axis. And then you see for any angle, we have a good agreement with the full simulation. So P/4 is here, is where we did the fitting, and 0 is here. I don't know if why we put on the right, but we fitted on two directions, here and here, and we get the rest as intrinsic information contained in the symmetry imposed in the elastic tensor.
The symmetry of this, because this is not really a demonstration that your fit is not theta dependent, because it's just one region.
Which is not, sorry?
Theta, if I call theta the incident angle. Okay, so what you say that because of the symmetry of the structure, the remaining parameter is theta independent, but I don't think this is true. Because this is not linked to the symmetry of the structure. If you have,
but in our model there is no explicit theta dependence. We have just elastic tensors, and we don't say anything about theta. We say they have a certain symmetry, and that's it. And so in that symmetry, for example, for the tetragonal one, we don't introduce an explicit dependence on theta. We say, okay, we have elastic tensors, we make the hypothesis.
No, I'm speaking about the fit, the inverse. So you start with the data at some theta value.
Exactly, but the fitting comes from the fact that now I'm choosing some form for my elastic tensors. So if I say they are tetragonal, here I will have 1, 2, 3 for this tensor.
Yes, but the data to
and then I have
value can depend on theta during the inversion. Because the data depend on theta.
I have to check if some of these parameters have to be checked, have to be fit on the 45 directions. I'm not even sure. Maybe we can do everything with the 0 direction. But if any, there is 1 or 2 parameters that we refitted on the 45 direction, but then the rest come in the sense, if there is one parameter, in any case, for example, the slope of the two curves, we fitted on the 0 direction, and we had for free on the 45. We didn't have to refit parameters. That was for free.
No, well, but I will not be too long, but just what I mean is that I know that you have enough data to fit your constant parameter.
Yeah.
But what my question was this fit? Can you find other parameter by choosing other data at other theta? Which will mean that your parameters are theta dependent.
Okay, I see the question, but I would say no, because in the end, making this fitting gives you, if now I take dispersion curves at 30 degrees and I plot them, they are good. I mean, so if I fitted my parameters at 35 to get the same, that would be good, and I would come to the same pictures I see here at 0.
Okay, thank you very much.
Thank you.
Thank you.
Thank you. Do we have a last question?
Yes, I have a question.
Yes.
It's about the transmission condition that you impose at the boundary with the homogeneous material.
In the micromorphic case.
Because of the duality. So you apply some continuity conditions, for instance, on the displacement or the traction force.
Mm-hmm.
So basically, it would mean that the results do not depend on how you cut your metamaterial. For instance, if you cut in the middle of elementary cell or on another boundary, the fact that it's continuous means that it does not depend. And there are some examples where the way you cut your material change the response of.
Definitely. This makes the pair with
on this.
Yeah, with the question before that, of course, close to the boundary, if you are cutting the cell in the middle instead that taking the whole unit cell, you will get a slightly different boundary behavior.
Okay.
But if you start taking a large enough sample, this should be not so widespread to make an enormous difference. But for sure, this is something to be investigated.
Okay. Thank you.
Thank you very much, Angela, for this very nice talk.
Thank you.
And
Thank you for the invitation.
You're welcome. So your presentation was recorded and it will be available for the others, or if you have any, if you have to listen to the presentation again, it will be available on our website. So thank you very much for your presentation, and thanks to the audience for being here.
Thank you. Thank you. Have a nice.
Very nice.
Merci.
Thanks a lot.
Thank you. Have a nice afternoon.